Hello students, welcome you all to the course of Compiler Design. In today's lecture, we will learn about Directed Acyclic Graphs. In short, it is otherwise called as DAG. When we are drawing the syntax tree, we faced some issues. In case there are repeated variable computations, if we have common sub-expressions, you were also pointing out to me when we were drawing the syntax tree, why are we repeating the computation and so on. So in order to eliminate that issue, we go for drawing this DAG, which is a directed acyclic graph, which can help us find out such type of common sub-expressions and other issues. So these are mainly very helpful in our code optimization stage. But now we will learn about DAG, and we can later, when we come to code optimization, we can again review this and see the effectiveness of using DAG for our code optimization. Directed acyclic graph is a special kind of abstract syntax tree. So last lecture we already saw about abstract syntax tree. Whenever we attach the context-free grammar with semantic rules, we get the abstract syntax tree. So based on that tree, we are going to now continue to draw the DAG. So in the second phase of the compilation process, we drew the syntax tree. And when we come to the end of the third phase, and as we move on to the fourth phase, we will be constructing this DAG, which is very useful for our code optimization. Once the code is generated, we can optimize it, or the syntax tree itself, we can draw the DAG and thereby optimize the abstract syntax tree, and based on that, the code generated is going to be optimized. So the characteristic features of a DAG are: each node of it will contain a unique value, and it does not contain any cycles in it. That is why it is called the name acyclic. So we are actually drawing a graph, and a graph is consisting of nodes and edges. So in every node we have to have a unique value. When we drew the syntax tree, we found that there were repeated values, but here we will not have that. So we will take examples and go through it. Before that, we will see the construction rule for DAG. So basically there are three rules. First of all, in a DAG, interior nodes always represent the operators. That is common. We have drawn the syntax tree. There also this is the condition. So interior nodes will be having the operators, and exterior nodes or leaf nodes will always represent the names, identifiers or constants. That is the variable names, identifiers or constants. And rule 2, while constructing a DAG, a check is made to find if there exists any node with the same value. So we are going to take one by one the node, and we are going to, for a variable, for every variable we are going to put a node, and if it is already existing, we should use that. So a new node is created only when there does not exist any node with the same value. So this action helps in detecting the common sub-expressions and avoiding the recomputation of the same, as I already explained. So rule number 3, the assignment instructions of the form x is equal to y are not performed unless they are necessary. So we will not be in the syntax tree, we will be representing such expressions. While we are drawing this, equal to will be the root node, x will be in the left side of the tree, y will be in the right side of the tree. But here we will not go for representing this equal to operator. Okay, so in other words, we will be drawing only the right side tree in a detailed manner. So these are the three rules we will apply to any given syntax tree, and we can convert it to a DAG. So we will follow the three steps and we will try to draw the DAG. So here there are cases. So we can have, when we are drawing the DAG, we are going to have operators. So we can have two operands and one operator. Case 1 is x is equal to y operator z. So we have three variables here and one operator. Or we can have a case 2 wherein we have only two operators and one operator and two operands. Or it can be simply an assignment statement. So if it is an assignment statement, then we may not be using a node at all. Only one node will be there. We won't be drawing a big diagram. So that is what is explained here. In step 1, if the y operand is not defined, then create a node y. Okay. If the z operator is not defined, we'll create a node as in this. So here we will be creating two nodes. As I already discussed, this equal to part we won't be dealing. So in case 1, we will create nodes for y and z. And in case 1, similarly, z will be the right child and y will be the left child. And we will have the operand in the middle as the root node. And so we will not have x. That is what we are saying. Remove x from the list of node identifiers. Add x to the list of attached identifiers for node n. In case we need that in the right hand side, we will be including it. I will go through some examples, then you can understand better. So here we have three statements, three address codes. Hope you remember how we wrote the three address code. So we are having T0 equal to A plus B, T1 equal to, can you tell me what is the expression? What is the expression for which this is the three address code? Yes, so we have an expression D equal to A plus B plus C. So that can be split as three statements when I am writing the three address code. So first of all, we are evaluating A plus B as T0, T0, and then that value is added to C, that becomes T1, and both the addition are assigned to D. Okay, so if I am drawing the syntax tree, I will draw accordingly. But here I will draw it in a different manner. So first of all, I am drawing for T0 equal to A plus B. So I am simply writing T0. I am not having the equal to symbol, you can see. So I am having A and B. The right side part alone I am drawing the tree. So A and B connected to the operator plus. And this particular answer is otherwise named as T0. Next we draw for the next statement T1. So I am continuing with the already existing diagram. Here I already have A, B added as T0. To this I am adding the value C. So I am putting a plus here and naming it as T1. Next, this has to be assigned, both of them have to be added and assigned to D. So I am pulling an arrow here to a plus. So I am adding T0 and T1, adding it. So the plus operator and naming it as D. Okay, so this will be the DAG. Here actually there are no repetitions. So we are having only unique values in the leaf nodes or the values. We will see other examples wherein we are having common sub-expressions so that we can appreciate the effectiveness or usefulness of our DAG. So here again I have A plus B, T1 plus C. So I'm and T3 is given as multiplication of T1 and T2. So instead of the plus operator, here I have multiplication. So first I found T1, then adding to that C, I get T2, and then T3 is nothing but multiplying T1 and T2. So you can get it like this. So this is even more complicated. We have more expressions. So T1 is A plus B, that is what we have drawn here. And then T2 is again A minus B. See here you have 2 times A and 2 times B. If I drew the syntax tree, I would get 2 times A and 2 times B in the diagram. But here we are not getting because we are putting A plus B here. For minus, again one more node I drew. So automatically I can draw the arrow. So I have A and B only once. So this particular T1 is for A plus B and T2 is for A minus B. And then I'm multiplying both to get T3. T3 is T1 into T2. And then T4 is T1 minus T3. So I'm putting a minus here. And finally T5 is T4 plus T3. Okay, so here I am having the advantage of eliminating the common sub-expression. I am not using the variable twice. So here it is unique. You can find that all the variables are unique. There are only two terminals, A and B. They are unique. But if I draw the syntax tree, it is going to be appearing twice. So this particular example, again, there is a common sub-expression, very much a common sub-expression. We have A plus B repeated. Okay. So now T1 is A plus B. And then it is, so A plus B is T1. So T1 is not written here. You can write here. So as I was telling you, this T1 is not represented here. You can might as well write it. Okay. So again we are adding, we have the next expression as A plus B plus C. So already we have A plus B. To that we are adding C. So we are getting the second expression also, and both have to be multiplied. So when I put like this, it is the understanding that we are taking A plus B as one direction, and in the next thing, since we are adding it to C, here we are having A plus B plus C. So this is the second expression. This plus will have all the three variables A plus B plus C, and then both we are multiplying. So this way all the leaf nodes are unique. But if I am drawing the syntax tree, you can try to draw the syntax tree. We will have A appearing twice, B appearing twice, and C will appear once. So that is avoided. Okay, so this way whatever sub expression is common. So here we are having A plus B as the common sub expression, and this has been eliminated. We are not recomputing A plus B. While drawing the syntax tree, we were recomputing A plus B. So here it is not recomputed. Already it is computed and the values are available, that we are utilizing it. So this is the advantage of drawing the DAG. If I am drawing the DAG, I am able to identify the common sub expressions and I avoid the recomputation of the same. Actually, I shouldn't have shown the answer, but you can see, appreciate it. See, there are so many sub-expressions. It is actually 2, 3, 4 times it is repeated. But and if you are drawing the syntax tree, you will have a 8 branches. This side 4, this side 4, and each time you have to compute. So we will be computing it 4 times, but here it is not needed. See, A plus A. Okay, A is common. So this particular arrow and this particular arrow at this point, it means it is A plus A. Okay, so when I'm writing here, it is nothing but A plus A. So one time it is done. And then when I move in here, this side is one A plus A, this side is one more A plus A. So here when I come, this side is covered. This two expressions are covered. A plus A is here, A plus here is here. So here we will get A plus A plus A plus A. Then when I come to this point, this side it is A plus A plus A plus A. Again this arrow it is A plus A plus A plus A. Okay. So you can appreciate it. So A here A plus A, and when you come this side, here it is A plus A plus A. So this is A plus A plus A plus A. And when you come here, it is A plus A plus A plus A. Here also the same thing. So we are covering the entire expression. And the variable A has been represented only once. So this is the advantage of drawing the DAG. We are able to completely eliminate any common sub-expression that is present in the given expression. So as we already noted, they are useful in determining the common sub-expressions used. And it will determine the names used within the block as well as the names computed outside the block. We are talking about the for loops and all. Each of them will be represented as a block. So we can easily identify which variables are within the block, which are outside the block. And then it determines which statements in the block may be computed outside. See, once computation is enough. So if it is outside, it will already get computed. So you don't need to do the computation inside the inner loop. Inner loop, outer loop, you know, no? So within the for loops, you don't need to compute. And it will describe what is the input, what is the output, what is the arithmetic operation performed for this code. So all this is very efficiently done. And several languages describe this method. They have option for the compilers. See, programming languages, each of the programming language has a compiler. And so these compilers mostly are equipped with this feature of developing or drawing the directed acyclic graph. And whenever we want to change also, once this graph is drawn, it is easier. The values while changing and doing modifications, it will be easier to tackle if we have a DAG. Okay, students, hope you can appreciate. So you can take all the examples what I've given. Initially, you can draw the syntax tree and then you can try out drawing the DAG. So you can appreciate how useful it is to draw the DAG. Thank you, students.